Okay, so let's continue. So we were looking at 1D Ising model in the last lecture. So I'll kind of do the recap of that, and then we'll kind of discuss some of the points that we had not discussed last time. So, so the 1D Ising model, we decided that we will use the transfer matrix method, and of course, we'll use that for 2D Ising model also, but along with transfer matrix, we'll also use some other technique that will simplify the system. But let's first understand the transfer matrix method here. So we begin with the Ising model with nearest neighbor interaction. J is taken positive, and H is the external magnetic field, and we choose periodic boundary condition for the system such that nth spin interacts with the first spin. Okay, that is how we did this, and then we wrote down a transfer matrix in this particular form. Okay, now if you write it in this particular form, the matrix doesn't seem symmetric. So there is one way of doing form of the metric which would look symmetric is to write half of beta h times s plus s prime. If you do that, then it is symmetric compared to what we had written down last time, which is like this. But that doesn't matter really. It would give you the same eigenvalues. Okay, it is just that you distribute one of the terms half and half between this transfer matrix and the next one, and so on. Okay. Anyway, so what we found was that with this choice, S and S prime taking plus or minus one value, you could write down the transfer matrix as a 2 by 2 matrix, and then you could kind of simplify that and diagonalize. Okay, because if
Sir,
you yes.
I think there will be sum over all spins. Last time Aman has pointed out this partition function.
Here.
Uh-huh.
Yeah. But I have written it in matrix form. That's what I was saying. If I
Okay.
write T in the matrix form, then there is a sum over all spins already. Okay, I don't have to write the sum again because it is all included in the matrix. Okay.
So,
Yes.
do we have systems or models where we consider some interaction like SI, SJ, SK, like tri-component thing?
Uh, yes, of course, you can study that kind of systems also. But those models need not be, may not be exactly soluble. Uh, so I can give you one example. There is something called chiral spin liquid. Okay, so it's a system where the spins are interacting with each other, but they have a specific kind of chirality. So imagine that you have a triangular lattice and you have three spins interacting antiferromagnetically. Then you could have a SI dot SJ cross SK kind of interaction. Okay, and that kind of interaction leads to what I was mentioning last time as what is called a frustration, because uh, the because of the antiferromagnetic interaction, the spins cannot all point in opposite directions or to each other on a triangular lattice. Okay, because if along one chord, if they are oppositely oriented, then the third spin has cannot make any decision whether it should be pointing up or down. Okay, so this kind of interaction, which is called the interaction induced due to frustration, is written like this: SI dot SJ cross SK. And people have studied models of that kind. In fact, about 20 years ago or maybe 30 years ago, they were good candidates for high TC superconductors. Okay. Yeah. So so you can, since it's a 2 by 2 matrix, you can compute trace, determinant, everything, and you can write down the eigenvalue equation and solve it. Okay, so we find this as two eigenvalues, and we basically said that the lambda plus is the dominant eigenvalue, and transfer matrix is diagonal in the plus minus basis, which represents the plus minus index on the eigenvalues, and not the up and down spin, which is the original basis in which transfer matrix was not diagonal. Okay, Now, of course, these states are orthonormals. Well, they are definitely orthogonal trivially because transfer matrix has been diagonalized, and because it is diagonal, off diagonal inner product would be just 0. You can normalize it to get it orthonormal state. You can write down transfer matrix in this particular form. Okay, and the advantage of writing it in this form was that if you take nth power of t, it just takes lambda plus to the n and lambda minus to the n using the orthonormality of plus minus states. And therefore partition function was very easy to write down because it was a trace. So you just take this state around and contract with plus and contract minus with minus. It just gives you lambda plus to the capital N plus lambda minus to the capital N. That is a partition function. Okay, and you can kind of use, since lambda plus is dominant, you can pull it out, and in the thermodynamic limit, that means taking n going to infinity, you find that this term is small and therefore does not contribute to the partition function. Okay, or let's say contributes, has a subleading contribution to the partition function in the large n limit. Okay, fine. So we can compute free energy, which is also something we did last time, and we said that that in the thermodynamic limit you can kind of say that this quantity goes to 1, and therefore your free energy basically corresponds to uh, the log of lambda plus times the nkt factor. Okay, fine. So since lambda plus is a function of j, h, and beta, and it is it is always positive definite, f is actually analytic. There is nothing, no non-analytic behavior is developed at any temperature except probably at beta equals infinity, that is 0 temperature. So therefore there is no realistic phase transition at any finite temperature in the system. Okay. Uh, so, yeah, so one could compute the average value of spin. Maybe I should call it spin because it could confuse with entropy. Uh, so, average value of spin, and that is also something we had computed last time, which was related to the local magnetization of the system. But you find that lambda plus is such that this expression actually is linear in H, and therefore the magnetization would vanish as the external magnetic field goes to 0. Okay, which is kind of consistent with what we had expected, that the system may not have spontaneous magnetization. Uh, we also had seen that uh, the free energy does not develop any non-analytic behavior, which is considered to be a signature of phase transition. Okay.
Sir,
Yes.
please explain the first line here. I mean, lambda plus is even function of h, and then we're expanding is this series expansion. This is not
Yeah.
clear to me.
Yeah. So,
This
yeah.
one.
Yeah. What is the problem? So, all I'm trying to say is the following: that lambda plus is an even function of h is something we know. Okay. Let's go back to the expression. Okay. So you can see it is a cos hyperbolic h and sin hyperbolic squared h. So h is going to minus h, for example. Lambda plus doesn't change sign. Lambda minus also doesn't change sign. But main point is that, like, since we are concentrating on lambda plus, you see that it doesn't change sign under h going
Yes.
to minus h. Okay. So if it is not changing sign under h going to h going to minus h, you can do a Taylor expansion of lambda plus around h equals 0. Right.
Okay. Okay.
So then the term linear in H cannot occur because H going to minus H symmetry would tell you that that term would have vanishing coefficient. So it directly starts at quadratic order. Is it okay? And now, of course, since the average value of spin is a derivative of lambda plus with respect to H, the magnetization is an odd function of H. And as a result, when H goes to 0, magnetization goes to 0. Okay, and that is the statement that there is no spontaneous magnetization. Okay. The susceptibility is, of course, derivative of the magnetization, and therefore you can kind of find this quantity by just taking the second derivative, and that is this expression.
I think this will be ln lambda plus in the magnetic susceptibility part.
No, 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 no. M also is just lambda plus. Oh, you mean there should be a 1 over lambda here?
Mm-hmm.
Yeah, yeah, yeah. Yeah, no, but it, yeah, okay. Yeah, that's right. Yeah, okay, I'll do that. Uh, okay. Uh, but anyway, main point of this exercise is that like uh, there is no spontaneous magnetization in the system. Okay. Uh, then we computed two-point correlation function, and we found by inserting the spins at appropriate places that this two-point correlation function can be computed in the basis in which t's are diagonal. That is the basis in which s is not diagonal, but one could still compute it. And the idea was simple. You write down the s in terms of uh, the sigma 3. Sigma 3 of usually is diagonal in the spin basis, but not in the plus minus basis. So you expand it in all possible forms in the plus minus basis, and then study the possible transitions at site S, at site I, and at site J, and that gives you this expression. Okay, for 1 point function, and it gives you a similar kind of analysis would give you this expression for 2 point function. Okay, uh, and uh, this particular term is the one where the spin, rather the state does not switch from plus to minus, whereas this is the expression in which the state switches from plus to minus from I all the way up to J, where it switches back to plus. And the state plus is the one which is chosen to be the ground state because lambda plus is the dominant eigenvalue, and therefore most of the chain would have spin state plus, except between I and J, where it could have been plus or minus, and those two configurations correspond to these two terms in Gij. Okay, then we massage this expression. We found that like the term where the spin doesn't swap cancels with the disconnected piece, and only the place where the state swaps from between plus and minus is the one which is a connected part of the correlation function. And then we wrote down the uh, correlation length, which is logarithmic function of the eigenvalues, and we showed that the Green's function or 2 point function falls off exponentially. Okay, uh, and yeah, so this is just inversion of that relation. Okay, so now of course we argued that the free energy is analytic at finite temperature, so therefore there is no phase transition at finite temperature, and at zero temperature you can only see phase transition if there is a level crossing. Generically in transfer matrix language, what one sees is even if you are looking at finite temperature phase transition, that statement corresponds to level crossing in the eigenvalues of transfer matrix. In our case, we have only two eigenvalues, lambda plus and lambda minus. But you may have more complicated transfer matrices in more complicated systems. And in that case, you may have multiple eigenvalues. And then anytime the lowest eigenvalue corresponding to the ground state becomes degenerate with the first excited state, okay, that is considered to be a signature of phase transition in the system when you look at the system from the transfer matrix point of view. Okay, so if that is a thing to look at, then we would want lambda minus to become equal to lambda plus, and such a thing would happen. Something we had seen actually. Maybe I can just go back. This will happen in the absence of external magnetic field, and uh, it would happen when the temperature is 0. Okay, so if magnetic field is set to 0 first, okay, and then you take the temperature to 0, then this piece would just go away, and only the first term would survive, and the first term is common for lambda plus and lambda minus. Okay, so at 0 temperature in 0 external magnetic field, you yeah, in that limit you can find lambda minus becoming degenerate with lambda plus. But if that happens, then you get log of 1, and in that case the correlation length diverges. Okay, and which is of course a signature of phase transition. Okay, that if the correlation length is diverging, then you would expect non-analytic behavior in the system. Okay, but this is a zero temperature effect. Okay, Fine. So let's try to study this system in a little different way. Let's do a low temperature expansion of the system. Okay. So, so by that I mean the following: that you treat that the system at zero temperature is in the ordered state. Okay, and then we kind of look at this system by turning on the temperature slowly and study thermal fluctuations uh, in that system. Okay. Now remember, what we have been arguing is that if you are studying system in thermodynamic limit, excuse me, then the dominant contribution to the partition function comes from the ground state. Okay. So therefore, if you are at zero temperature, then the most dominant contribution is going to come from the ground state. And therefore, what we will do is to look at the ground state of the system and ask, if I turn on the small temperature and treat temperature as a perturbation, how would the system evolve? Okay. Now we will assume that the ground state is consists of all spin up. Okay, say something like that. Okay, and we would kind of try to study the system. Okay, so so we, and main motivation for doing this is to ask a question that ground state is ordered state at zero temperature. Would it survive the thermal fluctuation or not? Okay, is it stable under thermal fluctuation? Okay, so as I said, we will assume all the spins aligned, and choosing them to be pointing up is just pure convenience. Okay, so when we say we are going to do perturbation theory, that means we really mean that we would write down states in which the spins are flipped compared to the ground state. Okay, so remember we had done this study earlier, that if you have all spins pointing up, then it would contribute some energy, that is the ground state energy. If one spin is flipped somewhere in the middle in the chain, then it has an energy which is ground state energy plus 2 times J. Okay, that is the additional contribution because of the nearest neighbor flipped spin interaction contributing extra energy. Okay, so clearly this state at low temperature would be the first excited state compared to the ground state, that which is completely ordered. And then of course the next state that one can look at is two spins which are flipped and so on. So that is, so our perturbation theory is based on number of spin flips relative to the ground state. Okay, is this okay? Hello.
Okay, sir.
Okay, so in that case, let's try to kind of look at this model in arbitrary dimensions. So let us assume that this model is on a d-dimensional hypercubic lattice. Okay, so remember, one-dimensional lattice or two-dimensional square lattice are simplest example of hypercubic lattices. And in one-dimensional lattice, if you pick a spin, you have two neighbors. If you look at two-dimensional lattice, if you pick one particular spin somewhere in the middle, it has four neighbors, nearest neighbors, because we are choosing a square lattice. Okay, so you can clearly see that the coordination number is 2D. Okay, so if you are in D dimension, if you have a hypercubic lattice, number of nearest neighbor spins is 2 times the dimension of the space. Okay, so what we will do is that we will utilize this fact that the coordination number is going to be 2D. Okay, and let's look at the system now. We define E to be the energy and G to be the degeneracy of the state. Okay, so let's first consider the ground state. Now, ground state is of course unique because all spins are pointing in the same direction, right? Okay, and that ground state would have energy given by E0, which is minus J times the number of spins times the coordination number by 2. The factor of 2 comes because, if you pick a spin, it interacts with its neighboring spin, but the neighboring spin is also interacting with this spin. So when you sum over all the configuration, every configuration is counted twice. So therefore you need to divide by 2. Okay, so that is the factor. Okay, is this clear? Every nearest neighbor interaction is counted twice in the state, so that's why we are dividing by 2. Okay, so let's go ahead and let's consider a state with single flip spin. Okay, so in this case, like of course all the spins are, we are in d dimension, we have n spins, all spins are pointing up except one pointing down. And how many configurations we have? Well, any one of these n spins could be pointing down, so therefore there are n configurations. Okay, so the degeneracy of this state is n. Okay, and the energy of this state is what we will call E1, which is E0 plus 2 times J times Z. Okay, as I said that in the case of chain, the factor would have been 2J, but now you would have additional coordination numbers, so therefore you would have the factor which is 2 times J times Z. Okay, so yeah. So next thing would be the state with 2 spin flips. And if you're looking at the state with 2 spin flips, you have 2 possibilities. Uh, One possibility is that you have 2 spins which are nearest neighbors and they are flipped, or the other possibility is that they are not nearest neighbors. Okay, so if they are, since our model contains only nearest neighbor interaction, if they are not nearest neighbor, that is good enough for us. Then they can be arbitrarily far away. It is same as them not being nearest neighbors. Okay, that's why it really corresponds to 2 distinct configurations. Either they are nearest neighbors or they are not. Okay, so let's consider that they are nearest neighbor spins. Now, if they are nearest neighbor spins, then what you are doing is we are looking for a pair of spins. Okay, nearest neighbor spins. Of course, a pair of adjacent spins which are pointing in opposite direction. Okay, so that would correspond to a degeneracy which is given by n times z by 2. Okay, so uh, first thing is that, like, you are looking for a pair. Okay, so therefore there are n by 2 pairs. Okay, but these n by 2 pairs on the d-dimensional hypercubic lattice has a coordination number z. Okay, so they could be arranged in z possible ways. Okay, so therefore n by 2 nearest neighbor spins with coordination number z will give you n times z by 2. Okay, is that fine?
Yes, sir.
Okay, so then let's look at the energy corresponding to that state, and the energy corresponding to that state would be ground state energy plus 2 times J times 2Z minus 2. Okay, so and the way to count this is to realize that uh, for every flipped spin you would have a factor of 2jz. That is what we wrote down. 2 spins would have factor 2 times 2jz. Okay, but then those two nearest neighbor spins actually have a gain in energy because they are pointing in the same direction, and therefore you need to subtract that factor. Okay, so that is the uh, energy. Okay, now uh, instead of this configuration, which is what I call A configuration, suppose you look at the B configuration where the spins are not nearest neighbors. Is there a question? Okay, maybe not. Uh, so yeah, so instead of nearest neighbors, suppose they are not nearest neighbors. Okay, if they are not nearest neighbors, then basically out of n spins you have to choose 2, so which is like n choose 2. Okay, but out of those n choose 2, nz minus n times z by 2 are the nearest neighbor configurations which you need to subtract. Okay, so total degeneracy for a state like that is n choose 2 minus the nearest neighbor degeneracy. Okay, so you can check that this can be written in this particular form, n into n minus 1 minus 2d by 2. So that is the degeneracy of double spin flip configuration when the spins are not nearest neighbors. Okay. So now what we'll do is uh, remember we said that like at zero temperature or in the thermodynamic limit, the most dominant contribution comes from the ground state. Okay, and everybody else has subleading contribution, of course, exponentially subleading contributions at finite temperatures. Okay, so just a second. So what we will do is that we will write down the partition function by explicitly writing down these configurations. Okay, that means a degeneracy of the ground state times the ground state contribution, degeneracy of first excited plus degeneracy of first excited state times the weight function for the first excited state, second excited state, and so on. Okay, so if you do that, then you get an expression which is like this. Okay, so let me kind of run through this one slowly. The first term is 1 times exponential of beta njd, and that was the ground state energy. Okay. So beta nj z was 2d, so njd times beta, of course, and minus beta and minus factor goes away, and that gives you plus answer. Okay. Now, remember that E1, E2, everything was written in terms of E naught plus some energy. So therefore, we can just pull E naught factor out. So that is the one which has been pulled out. So of course, ground state is unique. So that's why it gives you 1 plus the first excited state is n-fold degenerate. Okay, any spin could have flipped. Okay, and the energy is higher than the ground state energy by 4jd, and that's why you get this factor. Okay, then G2 has two terms. One term is nz by 2, which is same as nd, okay, which is this factor, and for that the energy is this, which we had computed from here. Okay, and you can write that as 4 beta j times 2d minus 1 factor. And other term had this degeneracy G2b n into n minus 1 minus 2d upon 2. Okay, and for that the energy is kind of different. You get the factor e to the minus 8 beta jd. Okay, that was also I did not compute it. Okay, but one can compute that also. Okay. Mm. It doesn't matter. Uh, it's kind of easy to compute this one because they are individual single flipped configuration. So you take single flipped configuration and just square it. Okay, so that is a factor. But I should have explained this. Okay, is that point clear? Hello.
Would you go through this expression again?
Yeah. So what I'm saying is the following: that I am writing the partition function as sum over states. Okay, and the sum over states with its degeneracy. Right? That is the usual way of writing the partition function. Okay, uh, the ground state piece is this one. Okay, first excited state, second excited states are pieces are written here, but E1 and E2 are written in terms of E0. Okay, so E1 is written as E0 plus some factor. E2 is also written as E0 plus some other factor. Okay, there's a E2B which I have not written down, but as I said, that E2B are two non-nearest neighbor spins flipped. So therefore, their energy is just 2 times the E1 energy. Okay, compared to the E0, the flip is twice as much. Flip energy is twice as much. Okay, so that's what we will do. I should have written it down. Okay, so now what we do is that we pull the e to the minus beta E naught out, and since E naught was minus nj z by 2, but z was 2d, so that's why njd, and the minus sign takes care of minus sign here. Okay, that factor is common to everybody, so you just pull it out. Then this quantity gives you 1 because G0 is just 1. G1 is n. That was the thing that we had computed. G1 is n. So so you write down n times the difference between E0 and E1, which is just 4JD. So that's why you get a minus e to the minus 4 beta JD. In case of E2, you have two contributions. One contribution, now remember E1, E2 is not exactly the energy contribution really. It's counting the number of spins. So therefore, E2 has two different energies simply because two different spin flip configuration have different energy. Okay, one of them is uh, this quantity, okay, which is what we computed here, that uh, that there is a uh, two spin flips uh, because of which you have energy 2z, okay, but because they are nearest neighbors, the two spins, the flipped pair is kind of nearest neighbor, and therefore there is a gain in energy because they are pointing in the same direction along the bond connecting those two spins. That's why there is this minus 2 factor of j. Okay.
So
Yes.
it should be -1, right? Because there's
Ah,
only one link between the two
yes,
spins.
yes. I was also wondering about it while talking this thing. So um, let me just check. Maybe it is just one. It should be one probably. It occurred to me also that like should have been. Okay, I'll take a look at it. I also feel that it should have been just one because I have written 2j outside this thing. Uh,
Yeah.
I can't think of. I can't think on my feet right away, but I don't see anything wrong in that argument. It should be 2z minus 1, I think. Yeah. Okay, let me check. Okay. Mm,
Okay.
yeah. Mm, fine. So modulo this kind of factor, it's okay. We'll worry about that later. Okay. Uh, you get a term like that, and then you get a term where two non-nearest neighbor spin has this degeneracy times twice the energy of single spin flip, okay, which gives you this factor. Okay. Does that make sense now?
Yeah, yeah.
Yeah. Okay. So now what we will do is we'll just for convenience define omega, which is e to the minus 2 beta j. Okay. And so that we can write down this expression in a little compact form. Okay. So now remember we have to take a log of this partition function to write down free energy. So here's the expression. Now there is a e to the minus, e to the beta n jd sitting around. So when you take a log, you take a log of this and a log of this entire parenthesis. Okay. So log of first term is kind of easy. The log of parenthesis is the one which is a little more tricky. Okay. So here's the expression. The first piece gives you this. Okay. This is a KBT, which is like 1 over beta, which takes care of that beta factor. And then you have a KBT times log of that entire parenthesis term. Okay. Now remember that this is the total free energy of the system. But what we want to check is what is the free energy density. That means free energy divided by N, which is a free energy per unit spin or per site, free energy per site kind of expression. Okay, so that would require us to divide this free energy by N. Okay, now that division is kind of easy here. Okay, first term is kind of trivial, but the other term, the N is sitting inside the log. Okay, so therefore it is not immediately obvious that the free energy per unit volume or per site, whatever you want to use as a language, free energy per site is independent of n is not immediately obvious. Okay, so what we'll do is we'll first check whether that is the case or not. Okay, so let's look at this expression and massage it a bit. Okay, so the first thing is that let's write down this expression as 1 plus sum over various quantities. Okay, so and those quantities I will call bk. Okay, whereas k goes from 1 to infinity really. Okay, that is a number of spin flipped. Okay, fine. So here this term is of course contribution from the ground state. This is a single spin flip, and this is a term which corresponds to B2. Okay, two spin flips. Okay, so so that is how the expression is going to be written. So let me write explicitly. B1 is going to be n times omega to the 2d, and B2 is n times d times omega to the 4d minus 2 times n into n minus 1 minus 2d upon 2 times omega to the 4d. Okay, fine. Yeah, I need this 4d minus 2 somehow. You know, this factor. Okay, I'll think about it and get back to you next time.
Yeah.
In my argument, I will need it actually. We'll see in a moment. Okay. So let's first consider this model in arbitrary dimension, and then we'll restrict ourselves to d equals 1. Okay. So first thing is that if you are working in arbitrary dimension, then I mean generically d is larger than 1. Thing, then you find that bk is much smaller than bk minus 1. Okay. Remember, omega is exponentially small, right? E to the minus 2 beta j. Okay. So therefore, if the next term is higher power in omega, then it is exponentially subleading compared to the previous one. So for example, this fellow is omega to the 2d, whereas this fellow is omega to the 4d or 4d minus 2. Okay. So clearly, if you go sufficiently high, if the growth is like this, the term bk is going to be much smaller than bk minus 1. Okay. So what we could do is the following. This term is of course B0. So you could say that B1 is smaller than B0, B2 is smaller than B1, much smaller than this thing. Everybody is exponentially subleading. So we could treat log as 1 plus some small quantity and just expand it. Okay. Now remember, we have done this computation, excuse me, we have done this computation up to 2 spin flips. Okay. So therefore, in principle, we can do the expansion of this log to reasonably high order. Our computation is reliable only up to 2 spin flip. So let's do the comparison only up to that point. Okay. But in principle, this computation can be done for k sufficiently large also. You know, like uh, for total number of spin n very large, k sufficiently large but not comparable to n, this computation in principle can be carried out. You can write a program, for example. Okay, it's not very difficult that way. But to do it analytically, I think few spins are good enough to just get a picture as to what is happening. So what we are going to do is we will utilize this fact and say that log of 1 plus x is equal to x minus x squared by 2 plus x cubed by 3 dot 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 kind of expansion we will use to simplify this expression, okay, and see what happens. Okay, fine. Now this particular thing makes a lot of sense simply because our omega is defined this way, and we are doing a low temperature expansion. Okay, low temperature expansion means beta goes to infinity. So if you have e to the minus very large quantity, then omega is a very small number. Okay, really. So in that case, all these quantities can be treated as very small compared to 1, and you can actually do this expansion. Okay. So since we know B1 and B2 reasonably well, we just expand that and we write down that as B1 plus B2, which comes from x, minus half B1 squared, which comes from x squared by 2. Okay. You of course get minus half B2 squared by 2 also, sorry, minus half B2 squared also, but that is not relevant because that would be related to some higher order pieces for which we need to know B3 and B4 and so on. So this is good enough. Okay. So if you are looking at d greater than 1, then b2 is of order b1 squared. Okay, so this is omega to the 2d and this is omega to the 4d. This is omega to the 4d minus 2, but roughly this quantity is still kind of close to it being square. Okay, as against d equals 1, where this doesn't happen, because if d is equal to 1 and assuming that this power is correct, this thing, then this goes as omega squared, and this also goes as omega squared. Okay, for d equals 1. Okay, so that is the reason why I think this power is correct actually. That is a crucial argument, point of the argument. Okay, that is why I said I'll get back to you on that. Okay, so this statement that b2 is of order b1 squared is true for higher dimensions, not really true for d equals 1. Okay, but let's work with generic dimensions. In that case, you can write down this quantity b1 plus b2 minus half b1 squared as this expression. Okay, so let's go a little slowly here. So just give me a minute. I'll just split the screen and show you the expression for b1 and b2. Yeah. Okay. So here's the expression for b1 and b2 on the lower screen. And in the upper screen, we see that b1 is n omega to the 2d, that is the first piece. b2 is nd omega to the 4d minus 2 plus uh, this entire piece expanded. Okay, so let's see how it is expanded. First term is n squared by 2 times omega to the 4d. Next term is minus n by 2 times omega to the 4d. The last term is nd, these two cancels, nd times omega to the 4d. So that is, these are three terms just expanded, expanding this expression. And the last piece here is b1 squared by 2, which is n squared omega to the 4d upon 2. Okay, so that is the piece. So now you notice that if you look at this expression, n squared by 2 omega to the 4d cancels. Okay, and as a result, this expression is actually linear in n. Okay, times some quantity. Fine. So what we can do is we can take this and put it back into the free energy expression, and you find that not only that the leading term, which is linear in n, but this term is also linear in n. Okay, and as a result, you can show that the free energy per site is finite. Okay, it is not an independent quantity. Fine, and the formula is like this. Okay, now let's consider the d equals 1 case. Okay, now like in this model where in arbitrary d, here also we'll consider that there is no external magnetic field. Remember, our omega was written in terms of only e to the minus 2 beta j, and there was no h really. So here also we'll assume that the external magnetic field is turned off. Okay, and if it is turned off, then we have computed the free energy using the transfer matrix method, and that is given by minus kbt times log of 2 times cos hyperbolic beta j. Okay, so okay, so in that case, what happens is that you have you can just expand this quantity for beta large enough. You have expression which is log of exponential times 1 plus e to the minus 2 beta j. Okay, now remember we had defined e to the minus 2 beta j as omega. Okay, so let me just go down. Sorry, I had to go up, I think. Yeah. So I defined omega to be e to the minus 2 beta j. So we can look at this expression and you find that this quantity beta would cancel with kbt, gives you minus j minus kbt times the log of 1 plus omega. Okay. So again, for small temperature, omega being much smaller than 1, log of 1 plus omega can be just expanded as omega plus higher order terms, and therefore your free energy per site would be minus j times minus kbt times omega.
So would you go 2 slides up?
Yes, sure.
Yeah, here only. Sir, up till this point, this expression is exact, right?
Yes,
And even for the one-dimensional case, what we have is exact, that cos beta h.
yes, yeah,
Why do they not seem to be matching?
yeah. So it is related to the same issue that we discussed last time, namely non-commutativity of the limits. N going to infinity and t going to 0 limit, you cannot kind of swap them around.
But we have done that, like while saying that, I mean, no, we haven't done that yet.
Yeah, we haven't done that yet. So I will argue. We'll see what happens here. Okay.
Okay.
So you get this factor, right? And this clearly does not agree with the formula derived in arbitrary dimensions. So uh, let's look at that formula. Oops. Yeah. Yeah. So this is a formula. So you would have expected the answer to be omega squared. Okay. Minus kbt times omega squared. That's what you would have expected. But what we get is omega in one dimensions. Okay. And this disagreement is actually related to non-commutativity of the orders of limits. Okay. So let's look at it from the transfer matrix point of view. So if you consider the transfer matrix for finite n, then you can write down the exact partition function. Remember, if you look at the eigenvalues uh, of the transfer matrix, then one eigenvalue is just cos hyperbolic beta j, and the other one is sin hyperbolic beta j. This is lambda plus, this is lambda minus. Okay, and therefore lambda plus to the n plus lambda minus to the n is this expression, which you can write in terms of either the beta nj, which is the dominant piece coming from both the pieces, and 1 plus omega to the n plus 1 minus omega to the n. Okay, so now look at the free energy, and you find that you you are getting this answer to be nj times n squared times omega squared, which is what you would have expected here. Okay. So what you're trying to do is to look at a system where n is taken to infinity later and t is taken to 0 first. Okay, that is the kind of behavior that one is looking at, or t is small and n is taken to infinity kind of later. Okay, whereas this limit is opposite. In this limit, you have already taken the thermodynamic limit first, and then you take the temperature going to 0. Okay. So what this is telling us is that the system actually has non-analytic behavior at 0 temperature. Okay.
When have we taken the temperature limit in the second transfer matrix case?
In the transfer matrix case, uh, well, in this case, if you take this limit, this term will of course vanish, because remember we had computed this energy, free energy to be minus j earlier itself, right?
Yeah, for the ground state part, but at
Yeah.
arbitrary temperature, this is exact, right? Even for the transfer matrix case.
Yes. Yeah.
Well, if not, I mean, we have written right now plus dot dot dot, but that above expression,
Yeah. Yeah. But those dot dot
1
dot
plus
are
omega
higher
to
order
0.
corrections. That is right.
I mean, yeah, we cannot say whether n square is larger because n goes to some infinity limit and omega is going to 0 exponentially, but that is
Yeah.
exponential in beta.
Yes.
We don't know which one will dominate, n or and that part of non-commutativity I can understand, but I don't know why we don't have an omega term yet.
In the transfer matrix case.
I mean, before taking any limit, we
Yeah.
should have some matching expression when both of
Yeah.
them are exact and we haven't
Yeah. But
taken any limit as
yeah.
such.
But here is the explicit computation. No, you can see that the terms which are linear in omega would just cancel in this.
Yeah, but
Right.
in the case but we can also solve the partition function by just writing it as, no wait, what?
This is a partition function, exact partition function. You expand
I
this, it is 1 plus n omega plus omega squared term, and this is 1 minus n omega plus omega squared term. Omega, the term linear in omega cancels, right?
wasn't the one-dimensional partition function just cos h beta j?
That is in the
It took the thermodynamic limit,
yeah,
right?
that is in the
When we were
thermodynamic limit, right?
calculating.
This is a finite n limit, right? In thermodynamic limit, of course, only cos hyperbolic beta j would dominate. So that is the point. That what is the limit that you take first determines how the system is actually behaving. Is that okay?
And we ought to take the thermodynamic limit first.
Yeah, I mean you have to take thermodynamic limit first in the system, right? And then you approach the temperature. Of course, you can. There is something called double scaling limit also you can do, but those are more kind of intricate systems. Typically, when you do single scaling limit, you take thermodynamic limit first. Okay.
Okay.
Okay. So that's why this computation did not agree with the. Uh, I mean, this computation of course agrees with the arbitrary dimension. This is a wrong statement actually, but it doesn't agree with the 1D computation that we did, which is a linear in omega. Okay, and that is the statement about non-commutativity. I need to correct this sentence. Okay. In addition, that at that if you take the thermodynamic limit later, okay, then you have a additional problem, and that is that like you look at this expression and you try to take n going to infinity, then your free energy per site is actually unbounded from below. Okay, because this quantity is kind of arbitrarily negative uh, in this case. Okay, and as a result, you find that your ground state is not stable at finite temperature. Okay, and that is the same statement as the system doesn't have long range order, because uh, you can kind of lower the free energy by generating the spin flip configurations. Okay, and this is something which reconciles with the earlier entropy versus internal energy argument that we had given, saying that the system would prefer to generate, rather proliferate the interfaces uh, in the system so that it can lower the free energy of the system. Okay. So this is clearly a issue of how you take these limits. Okay. Now, of course, if you take temperature going to zero limit first, then there is no such term occurring at all. You have a fixed free energy, and then the free energy per unit per site is also a fixed number. Okay. And in that case, of course, you need to only worry about how whether there is a level crossing at zero temperature. Okay. Is that fine?
Yeah.
Okay. So now let's go over to 2D easing model. Okay. But uh, yeah. So so before we actually do 2D easing model, we kind of do a small detour of the 2D easing model itself, but not really solve 2D easing model to start with, but try to create an argument which would try to show that maybe the model doesn't have any transition. Okay. So uh, to start with, of course, the mean field theory approximation that we had studied seems to suggest that the system should show phase transition at some finite temperature. Okay. The other argument that we had given in while talking about no phase transition in d equals 1, we also gave an argument as to why there is a phase transition in d equals 2 by doing the same study of coordination number and stuff like that. And we found that entropy versus internal energy argument also favors phase transition at some temperature greater than 0. Okay, so there are some indication which tells us that the system would undergo phase transition at finite temperature. Okay, and and none of these just a second. And none of these arguments refer to any specific choice of lattice. It is, we didn't say that it has to be a cubic lattice or anything like that. Okay, or square lattice, since we are talking about 2D Ising model something. Okay, this was just generic argument about how many nearest neighbors you could have, and just do the counting with respect to that. Okay, fine. So let's, for the argument's sake, consider a square lattice. Okay, so we'll start with a square lattice system. Okay, and we kind of uh, let me draw it this way. Okay, so let me uh, remove this thing. Uh, I have not been able to edit this file, didn't get enough time to do that. So I think this image actually goes out of the screen. So, so let me first shrink it and show it to you. But I think whatever you see is good enough. Maybe I'll shrink the image further so that it fits the page, but that's not important right now. So this is a square lattice that all of you would agree, right? I mean, this is how we uh, draw a two-dimensional square lattice. And I want to do the following thing, pick a particular point and call it 0. Okay. And then you kind of connect 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. Okay. You label them in with respect by using positive integers. So this red line is kind of successively increasing positive integers. Okay. It would it would go down to a next line and so on. Go back to 0 and go to the right, and you label that -1. Okay, and then you go down 2, 3, 4, 5, and so on. Okay, and you can kind of keep numbering them as negative numbers. Okay, and it goes like that. Okay, now you can see that if you kind of draw it in this particular fashion, then you have actually touched every lattice sites. Okay, and this, of course, dot dot dot, it will go continue going like that. Okay, so it will kind of go here, then go down, and so on, and this fellow will kind of go here and go up and so on. Okay, is that fine?
Yeah.
Okay, so every if you take red and the green line together, then you have actually touched every lattice site. Okay, now let's kind of use this red and green line depiction to rewrite the Ising model Hamiltonian, where ij are nearest neighbor interactions in the original square model. Okay, uh, in terms of the linear chain, this is a chain, right? Red connected to green, sorry, at one point. So you can just say that this goes from minus infinity to plus infinity, or minus n to plus n, whatever is the size of your lattice. Okay, with all negative fellows painted green, all positive fellows painted red. Okay, if you do that, then you have a linear chain, and the Hamiltonian is minus summation over n prime j n prime s n prime. Okay, now notice one thing, that the two-dimensional two-dimensional Ising model Hamiltonian had a nearest neighbor interaction, which is what that angle bracket tells you. Ij are nearest neighbors. Okay, here I'm not calling n and n prime nearest neighbors at all. I just say it's a linear chain because it is just one-dimensional object. But you see that the interaction is like this: 0 interacts with 1, 0 interacts with -1 also, but 0 interacts with 3 also, and -3 also. Similarly, 6 interacts with -1, -15, 5, and 7, and so on. I mean, you can look at any such thing. Suppose you look at 8, it interacts with 7, 9, 17, and 19. Okay, so clearly this j and n prime, unlike this j, cannot be kept outside the summation, because depending upon whether n and prime are the numbers to which there is a coupling or not, okay, we'll have to decide whether you put this term at all or not. For example, there is no interaction between, say, 4 and 6, sorry, -4 and -6, okay, or 4 and 6 for that matter. Okay, similarly, there is no interaction between, say, 4 and -10. Okay, So therefore, if you choose n to be 4 and n prime to be minus 10, there is no terms of that kind. Okay, but nevertheless, there is a interaction between 4 and minus 11. Okay, so you have a Hamiltonian for a chain in which you don't just have nearest neighbor interaction, but you also have some kind of a long range interaction. Okay, how is that long range interaction? Well, it depends upon how this stuff spans out, right? So one interacts with minus 6, okay, but minus 5 doesn't interact with 1, okay, something like that. Okay, so but effectively this is a Hamiltonian for a 1D Ising model, right? And we have just argued that one-dimensional Ising model has no phase transition at non-zero temperature. Okay. Now contrast that with the earlier argument that we just gave, that both mean field theory approximation as well as the entropy versus internal energy argument tells you that there should be a TC, finite value of TC, non-zero value of TC, at which you should see a transition in this system. Okay. But clearly, as you can see, this two-dimensional system can be written purely as a chain, and this 1D Ising model would say that there shouldn't be any transition. Okay. So how do we reconcile this fact that this Ising chain and therefore no phase transition versus a 2D Ising model is likely to show phase transition using, say, for example, entropy versus internal energy argument. Okay. So maybe I should increase now. Okay. And the catch is, of course, in the long range interaction. Okay, so the model has long range interaction when you write that as a chain model, whereas it has a nearest neighbor interaction when you write that um, as a 2D Ising model. Okay. Uh, in addition to that, we also find that the interaction J and N prime is, oh, this should have been comma. Uh, uh, the interaction J and N prime is not translationally invariant. Okay. So, for example, if there is a interaction between 1 and 6, okay, 1 and minus 6, sorry, if there is an interaction between them, there is no interaction between minus 5 and 0, okay, or anything minus 5 and 2, okay. So this is the distance between this is 7, distance between this is also 7, but while this has interaction, this doesn't. Okay, so there is no clear-cut statement about translation invariance in this interaction. Okay, fine. So that statement corresponds to a statement that J and N prime is not equal to J times N minus N prime. Okay, which is what you would have expected if it was translationally invariant. That if this interaction was there, then this interaction also should have been there. Okay. Fine. Similarly, minus 7 to 0 or something like that. Okay. So just to kind of clarify this situation, suppose we consider a model with a long range interaction. Okay. So suppose we consider a model where J and N prime is J upon N minus N prime to some power 8. And we assume that A is positive. That means as the distance increases, the interaction goes down. Okay. Now, our model actually doesn't have it that way, because here the distance is, sorry, here the distance is 7, here the distance is 1, okay, but the interaction is same. Okay. Similarly, here the distance is like 11, 33, and interaction is still the same, right? 11 minus 22. So it's like 33, but the interaction is still same. Okay. So the example that I'm trying to consider is not of this kind at all, actually. But nevertheless, if you try to consider a long range interaction in a 2D system, okay, and suppose you write it in this form, okay, and assume A to be positive, that means it is actually falling off as the distance increases. Okay, we can ask a question whether a system with this kind of interaction, whether it has phase transition at all. Okay, Does that make sense? Is the question clear?
Yeah. So this phase transition will also depend on A, the power law behavior, or will it be the same for all A?
No, 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 no. It won't be. In fact, we will find constants on it.
Okay.
So hopefully today I think we'll reach it. Just 2 3 slides are left, so it should be possible. Okay. So yeah. So what we are going to do is to find an argument for A. I mean, find a range of A for which the phase transition will not be possible, and find a range of A for which it will be possible. Okay. That is the exercise today. Okay.
Yeah.
Any other questions? Okay, if not, let's go ahead. Let's assume that this is the kind of interaction with A positive. Okay. A negative kind of doesn't make sense because it's like a non-unitary thing. As the distance increases, if the interaction increases, it would kind of system would tend to collapse in a situation like that. Generically, you see kind of avalanche type behavior in the system. Okay. Stability is something where you would rather expect A to be positive. Okay, so let's consider this in a chain model picture. Okay, long range interaction, and let's consider an interface, and the interface is like this: that all the spins Sn are taking value +1 when n is positive. That means anything which is, I suppose, red colored in our picture. Okay, and all the spins which are 0 or negative, okay, would take value -1. Okay, so that is the green line. Okay, so now we could ask, what is the energy of the interface? Okay, the energy of the interface is related to the J factor, and that is sum over all m's, sum over all n's. Okay, one of them of course goes from 0, the other goes from 1. Okay, so slightly different sums. Okay, 2j upon m plus n. Why plus? Because the quantities which are computed along the red indices or maybe green indices are negative. Okay, so therefore n minus n prime actually becomes m plus n. Okay, okay, to the power a. Since it's a mod, it doesn't matter. Maybe it is minus m minus n, but it doesn't matter really. Okay, fine. So what we'll do now is that we will take this m plus n factor and try to define a vector r by treating m and n as going back again to a two-dimensional system, and think of this as a two-dimensional lattice. Okay, uh, kind of parameterized by ordered pair mn. Okay, so it kind of think of a vector r going from origin to this point. Okay, fine. So since m is positive semi-definite and n is positive, it tells you that the r vector is pointing in the first quadrant, right? Because both these entries are positive or positive semi-definite, you are in the first quadrant. Okay, when m is equal to 0, you will be along the x-axis, but it doesn't matter. Sorry, you will be along the y-axis, but it doesn't matter. Okay, so you are essentially uh, uh, in the first quadrant of the two-dimensional space. Okay, fine. So if you are in the first quadrant, then what you could do is you can write down r vector as r times cos theta comma sin theta. Okay, this is just kind of polar representation of that vector. Okay, and if you do that, then you can replace this double sum by a double integral on the first quadrant. Okay, so the interface energy can now be written as integration from 1 to sorry, this should have been infinity. Just give me a moment. Yeah, should have been infinity, sorry. So this integration should be from 1 to infinity. A lot of terms missing actually. Okay, I think there's a typo in my, just give me a second. Yeah, I forgot to put a space in between two terms. That's why it kind of messed up. I suppose I think it will work now. That's right. Yeah. So uh, between infinity and r, I did not put space. That's why it just kind of ignored the entire expression. Okay. So this is the integral 1 to infinity r dr. And the integration on the angular variable goes from 0 to pi by 2 because you're in the only in the first quadrant. Okay. And then m plus n to the a can be written as r to the a times cos theta plus sin theta whole to the a. Fine. Okay, just using this representation of mn as r cos theta and r sin theta, you just plug it in. Okay, fine. Now what we'll do is that, like, you have a cos theta plus sin theta. It's a bit of a nuisance for this integral, but easy thing to do is to kind of shift this integral to minus pi by 4 to plus pi by 4. If you shift this range, then this quantity just becomes cos theta. Okay. Okay. So the advantage of kind of rewriting this in terms of a shifted variable is that if you write this, I mean, it is same as just shifting the uh, theta variable. Okay, but if you do that, then you can get this expression which is like this. Okay, fine. So once you do that, then this integral is doable in principle. Okay, but that's not very important for us. What is important for us is the radial integral. And radial integral has a power because of r dr and r to the a. It is dr upon r to the a minus 1. Okay. Are you with me with this?
Yeah.
Okay. So, so now we just concentrate on the radial part of the integral because that is the one which goes to infinity. This thing uh, should have been 1 to infinity. So sorry for that also. Um, so now clearly if a is less than 2, okay, less than or equal to 2, say, for example, if r is equal to, sorry, a is equal to 2, then you have dr by r. And if you do that integral, you get a log r. And log r, of course, the lower bound is 1 really. Sorry, because it was 1 to start with. M and n take values which are minimally 1 basically. So, uh, I mean, the one quantity, I mean, remember, even if one of them is 0, the other one is minimally 1. Okay, so the length is at least 1, so it cannot be 0. Okay, so that's why this integral starts from 1. So so log of r with 1 gives you 0, but log of infinity gives you divergent answer. Okay, and any power which is less than 2, okay, would put higher powers of r in the numerator, and therefore that would also diverge. Okay, so therefore if a is less than or equal to 2, okay, the energy of the interface would diverge. Okay, on the other hand, if a is greater than 2, then the energy of the interface is finite. Okay, if the energy of the interface is finite, okay, then then the entropy will always win over the internal energy, because internal energy contribution from the interface is small, and you can make more and more interfaces to lower free energy, and that would increase the entropy of the system, but it will always dominate. Okay, and as a result, if a is greater than 2, you won't see any phase transition. Okay. On the other hand, if A is less than 2 or less than or equal to 2, then the interface energy would scale. This is just kind of, dimension counting thing, would scale as L to the 2 minus A, uh, where L is the length of the chain. Okay, so if that 2D system written as a chain, or you just think of chain with a 1 over R to the A kind of interaction, then the interface energy would scale as L to the 2 minus A. Okay, this is just a scaling statement about dr by R to the A minus 1. Okay, fine. So if A is between 1 and 2, okay, so if A, that means 2 minus A is smaller than 1, okay, that's what I mean by A between 1 and 2, then the interface energy is L to the some power which is smaller than 1, and therefore scales slower than the length of the chain, which goes as L to the 1. Okay, length of the chain goes as L to the 1, whereas the interface energy goes as L to the smaller power than 1. Okay, that is the statement. Okay, fine. In this case, it would exhibit a finite temperature phase transition. Why? Because the system would have its internal energy going as L to the 2 minus A, whereas its entropy would go as log of L. Okay. So, what you can show in this case is that there is an interplay available between the smaller power at which the internal energy could scale versus a power at which the entropy could scale. Okay. On the other hand, if you take A smaller than 1, then L to the 2 minus A would grow faster than the size of the chain. Okay. And if it is going to grow faster than the size of the chain, then again there won't be any phase transition, because in that case entropy is just log L. Okay. And uh, and the internal energy is growing much faster because it is going as L to the power larger than 1. Okay, so therefore entropy can never win over internal energy, and therefore you will always be in one kind of phase. Okay, so what one concludes here therefore is that if you take long range interactions, then if the long range interaction has a fall off between 1 over R to the 1 plus epsilon, okay, where epsilon is smaller than 1, then the system can have phase transition. Okay, when epsilon is equal to 1, that means A is equal to 2. Okay, in that case also system would have phase transition. In fact, this has been worked out by Kosterlitz, and it's an interesting computation. But this result that A should be between 1 and 2 goes back to Dyson. Dyson has kind of proved this result rigorously, showing that if A is outside any of these ranges, in fact, he has equal to sign, but he doesn't have exact result for that. But he could not rule that out. But he said that like if A is greater than 2 and if A is 1 or less, the system cannot exhibit phase transition. Okay. So if one considers long range Ising model, this is the result that you would see in this system. Okay. This is a chain. Okay. Remember, it's not a higher dimension Ising model. It's a Ising chain with long range interaction. Okay. So I think I'll stop here today. Any questions? Hello.
So when we try to model the 2D chain structure as a 1D chain,
Yeah.
like each point has 4 neighbors.
Yes.
2 of them are just consecutive, so that will
Yes.
appear in the J term,
Yes.
and 2 of them will be some distance apart. And generically, if it's an arbitrary point, it can be arbitrarily far away because
Yes.
it
Exactly.
can that is growing in size, the
Yes.
spiral.
Yes.
So it is hard to model it with a container structure
Yes,
like 1 by n minus n prime.
yeah, I agree.
So we need something that spikes at very small points and spikes at some medium points and then falls off
Yes.
again.
Yeah, exactly. So, we are not going to solve this model in this way. It makes no sense to do it in this fashion. But this was just to kind of, provoke by kind of giving an argument that, like, if you want to call this as a two-dimensional system, it can also be modeled as a one-dimensional system. You know, then how are you kind of going to say that 2D system should have a phase transition? Okay. So this is just to provoke. Nobody is going to actually use this method to kind of try to solve this model. It's much more messy doing this way. Okay.
Yeah.
But I mean, so all I was trying to say was that, like, if somebody says that, like, okay, we have rigorously proved that 1D model doesn't have transition, I can always bring the 2D model look like a 1D model. How can you argue that it doesn't have transition? That is a kind of, and just so today's class was just to give a counter to that, saying that, like, if you have long range interactions, this is total mess, because this is a long range interaction not even falling off as a distance. Okay. But even if you take something falling off as a distance, okay, you can actually put constraints on what are the models which could actually undergo phase transition, and the other class of models cannot even have phase transition. So you take j n minus n prime to say cube, that model cannot exhibit phase transition in the chain. Okay. So that is a point that I wanted to get at before starting to do 2D easing model. And this was more of a pretext to kind of talk about the long range model, and not so much of, even trying to attempt to solve a model in this form. In fact, out of question, we are not even going to do something like that.
Yeah, okay.
Any other question? Okay. If not, can we close the session?
Sir, can you upload the slides?
Oh yes, I'll do that.